Good morning, students. In the last lecture, we derived the maximum velocity of a vehicle when vehicle is moving along a circular horizontal track. Then we derived the minimum velocity of the vehicle when it moves along a horizontal circle of vertical wheel of date, that is maude ka kuwa. Now, the next important question for 12th standard rotational dynamics chapter is we have to derive the maximum velocity of a vehicle when vehicle is moving along the circular track, but that track is not a horizontal. That track is banked. Banked means what? It is tilted. It makes this road makes an angle of theta with whom? Horizontal road. Makes an angle of theta with horizontal road. This particular surface is called inclined surface. So we observe that this particular vehicle is what? Moving along this bank road. Now we are going to consider a vehicle of mass m. So what is m? Is a mass of the vehicle. Mass of the vehicle. This theta is called angle of banking. We observe that if I consider its own weight of the car is always moving in the downward direction. So here mg represent what? Its own weight. Own weight, we can say weight of the car. It is always in downward direction. Since car or vehicle is on the bank road, this red line represent its normal reaction, and this normal is always perpendicular to the surface of the road. This normal is always perpendicular to the surface of the road. And if I apply the geometry, we observe if this is theta, this is 90, agree? This will be what? Theta. If I apply the geometry, you can see. So we can resolve this n into two components. One is vertical components and second one is what? Horizontal component. So students, vertical component of this particular normal reaction is given by n cos theta, and the horizontal component of this particular normal reaction is given by n sin theta by geometry. So we observe that we are going to consider when car is what moving along the bank road, we are going to ignore the frictional force provided by this bank road and other conservative forces like air resistance or those things. So we observe that this n cos theta is one of the force is balanced by whom? Its own weight. So from this particular statement, we can equate n cos theta equals to what? Mg. The students, and we observe that there is a horizontal component n sin theta. This horizontal component will help to rotate, or we can say move this vehicle along the bank road. That bank road is what? In circular track. So we observe that this n sin theta will provide what? Necessary centripetal force. So students, let us complete the derivation. So we observe that here n vertical component, what we have taken here, students, n cos theta. So I am going to write here the vertical component of n is what? N cos theta. Horizontal component is what? N sin theta. From the diagram we observe that n cos theta is balanced by mg. The vertical component is balanced by its own weight mg. So what is the vertical component here? N cos theta is balanced by what? Mg. This is say equation number 1. As I told you, horizontal component will provide necessary centripetal force. So what is the horizontal component here, students? N sin theta, which provide necessary centripetal force. Students, centripetal force, formula for centripetal force is what? Mv square upon R, where R represent what? Radius of that particular circular track. Students, I'm going to divide 2 by 1, means 2 divided by 1. If I divide 2 by 1, to n sine theta divided by n cos theta will give us, what is the second equation ka right hand side? mv square upon r the whole divided by m multiplied by g. This get cancelled, nn get cancelled. So what is sine upon cos, students? We observe that sine upon cos is tan theta equals to what? V square upon rg. So students, if I shift rg term over there, so rg multiplied by tan theta equals to what? V square. And if I take the square root, so what is the velocity along the bank road is given by V equals to under root of rg tan theta. This expression gives us the most safe speed on the bank road. Thank you very much.